Fick's first law. There are actually two laws, Fick's first law of diffusion and Fick's second law of diffusion. Here in this video I am going to discuss only the first law. This law was discovered in 1855, means this law was formulated in 1855 by the physicist Adolf Fick. Okay, this law is about a physical process which is known as diffusion. Diffusion is a process of mass transfer. Okay, if in a medium, the medium may be solid, it may be liquid, again it may be gas also. So whatever be the medium, if there is a concentration gradient, means if there is a difference in the concentration of the substance in that medium, okay, then diffusion will take place. That means transfer of mass will take place. And that physical process can be governed by using this equation. Of course, there is one condition. The condition is steady state condition. If there is no change with of any parameter with respect to time, then only this equation, means Fick's first law of diffusion, can be used. And if there is any time dependent parameter, in that case you have to go for the second law, that is Fick's second law of diffusion. So here in this video I am going to discuss only the first law. Okay, experiments were done, and by analyzing those the results of those experiments, this law was formulated. This law is written as this way: J, this is equal to minus D into dc dx. Can you see? J is equal to minus D, capital D, dc dx. Okay, what is J? J is called diffusion flux. This is measured in amount of substance per unit area per unit time. That is called diffusion flux. Amount of substance, this amount can be expressed in molar terms also. Okay, if you want, you can express in kg, means mass. You can use mass also as the amount of substance. Okay, again you can use molar concentrations. So J is nothing but amount of substance, means diffusion of amount of substance per unit area per unit time. And J, that is the diffusion flux, this is a vector quantity. This is not a scalar quantity. This is a vector quantity. Okay, and here I have written the equation for only one dimensional case. You can see here x is there. X is the spatial coordinate. If you talk about two-dimensional case or three-dimensional cases, means more than one dimension. If more than one dimension is involved, in that case you can use the vector equation like J is equal to minus D nabla C. Nabla is a vector operator, nabla or del. Okay, this is a vector operator, and this is a vector. Okay, J is a vector. J is a vector quantity. D, this is what? This is called diffusivity or diffusion coefficient. Okay, diffusivity or diffusion coefficient, unit of which is area per unit time. So in SI unit it will be meter square per second, square meter per second. C is nothing but concentration gradient. So C, it is amount of the substance per unit volume. Okay, amount of the substance per unit volume, that is the concentration gradient. And dc dx, this represents concentration gradient. C is concentration, dc dx is the concentration gradient. Here nabla C appears for two or three dimensions. You have to use this equation. So here nabla C, this is also nothing but concentration gradient. Nabla is what? That is known to you, I think. Nabla is equal to I del del x, I cap. I cap is the unit vector, plus j del del y plus k del del z. Okay, here x, y and z are the spatial coordinates along x, y and z axis. Means if you use Cartesian coordinate system, in that case, nabla will be like this. And I cap, j cap and k cap are the unit vectors along x, y and z directions. Okay. So this is the mathematical formulation, and of course there minus sign must be there. You need to use minus sign here because dc dx, this is negative, but we know that we are talking about diffusion flux, so which is a positive quantity. So to make the left hand side positive, we have to include one negative sign in the right hand side of the equation. Otherwise, if you do not include this minus sign, then the right hand side will be negative, because dc dx is always negative. Okay, mass transfer takes place in the direction of negative concentration gradient. Means suppose mass transfer is taking place, this is the x direction, and this is point number 1 and this is point number 2, and direction of mass transfer is this. That means concentration at point 2. Okay, say this is being represented by C2, concentration at point 2 must be less than concentration at point 1. So what, and suppose this distance, this is what? This distance, coordinate of point 1 is, suppose it is x1 and coordinate of point 2 is x2. Okay, then in this case dc dx will be equal to what? It will be equal to c2 minus c1 divided by x2 minus x1. x2 minus x1, this is positive, but c2 minus c1 is negative. So dc dx becomes negative. Again, this d, this is also a positive quantity. So this negative quantity multiplied by this positive quantity will give negative result. So to make the right hand side positive, we have to include one negative sign. Okay, so for one dimension, this is used. This equation is used. And for 2 or 3 dimensions, this is used. Say, in your given problem, the problem is, say, 2 dimensional. In that case, you don't write the last one. Use only x and y, means I cap del del x plus j cap del del y, which is nabla. Okay? It is an operator. If you have studied mathematics, then means if you have studied vector calculus, then you must know this thing. Anyway, so, and you will find applications of this diffusion process. This is nothing but a physical process. Okay? And what is the driving force here? Driving force is the concentration gradient. If concentration gradient exists means a non-zero value. Okay, if concentration gradient is 0, that means there is no difference in concentration. Okay, in that case, diffusion will not occur. But if it is a non-zero quantity, if diffusion gradient, concentration gradient is a non-zero quantity, in that case, diffusion will occur. Okay, so here the driving force is nothing but the concentration gradient. If concentration gradient exists, then diffusion must occur. In the subject of biology, you will find this process. Say for example, transfer of oxygen from bloodstream to tissues. Again, transfer of carbon dioxide from tissues to bloodstream. This is nothing but diffusion process. In case of material science, you will find this diffusion process. Diffusion of dopants in semiconductors. Okay, you know that for electronic devices, semiconductors are required. And in case of semiconductors, dopants are used. So, in that case, the process of diffusion, help of the process of diffusion is used. Again, in case of chemistry, okay, for the separation techniques such as distillation, okay, this diffusion process is used. So, in case of chemical engineering, you will find this, find the application of diffusion process. So, many areas of engineering and technology are there where the process of diffusion is used. Okay, so this was all about What? This was all about Fick's first law. But if, and here the concentration gradient, this is a fixed value. Sorry. I am extremely sorry. I am talking about this D, diffusion coefficient or diffusivity. This is not time dependent. This is time independent parameter here in this case. Okay. But if the D, diffusion coefficient becomes time dependent, then in that case you have to use Fick's second law. Okay, not this one. Okay, so this was all about today's lecture. The topic was Fick's first law of diffusion. Okay, so this is the end of this video. Thank you for watching this video.